Previously, we worked some examples using thermometer data. This data set had a mean of 0 and a standard deviation of 1, just the same as the standard normal distribution. Because those parameters were the same as the standard normal, we could use the TI-84 function, the normal CDF, cumulative density function, and then we put in our low or minimum number and high or maximum number on the number line to get that area or the probability that we were interested in. And we could do that directly with the data set for these thermometers because they had a mean of 0 and a standard deviation of 1. Well, obviously most data sets don't have a mean of 0 and a standard deviation of 1. Recall we did some work with adult male heights, and the mean was clearly not 0. The mean height was 69 inches and the standard deviation was 21.8 inches. So what do we do when we have a data set like that? And that's what we want to figure out today. So to use the standard normal functions, what we have to do is standardize our values by converting them to z-scores. And we've seen z-scores before. Remember, the formula for converting a value to a z-score was x minus the mean. Now we may have a sample mean. We've seen that before over the standard deviation, but what we're going to be seeing now are population mean. So x minus mu over sigma. It's the same calculation, only now we're using the symbols for population mean and population standard deviation because that is what will be given. But we have used this one previously, using sample mean and sample standard deviation. So this is the formula we'll be using, and we want to round z-scores to 2 decimal places. Now, what is x? We're talking about the mean being mu and the standard deviation being sigma, and x is our value of interest. So there'll be some value we're interested in, and we'll want to know what's the probability that we would be above this number, what's the probability we'd be below this number, or it may be the probability where it's between this number and another, and we'd be calculating 2 z-scores. Now, z has no units, so we don't report units on a z-score. It just represents the number of standard deviations x is above or below the mean. So z represents the number of standard deviations our value of interest x is above or below. I'll just put above, below, slash below, because it could be above, it could be below the mean. That's what a z-score tells us. Okay, so once we standardize the data, that means the mean will be 0 and the standard deviation will be 1. So we actually did something like this before, looking at a normal distribution and standard deviations. This is that problem we looked at with our mean heights of adult males, or a height of adult males. It's a normally distributed data set where as we said, the mean was 69 inches and the standard deviation 2.8 inches. And what we did before, I've reconstructed here what we did before. We put our mean on our number line, and then we just added 2.8 to get to the first standard deviation above the mean. So we added 2.8 to get here, we added another 2.8 to get to 2 standard deviations above the mean, another 2.8 to get to 3, and another 2.8 to get to 4. And then we did the same thing here, only now we're subtracting. Minus 2.8, minus 2.8, minus 2.8, minus 2.8. So now we know the heights that are right on these exact z-scores. but not every height, that we might be interested in is going to hit exactly on one of these z-scores. So what we were looking at previously was two different people. We had LeBron James at 80 inches and Danny DeVito at 60 inches. And so what we did before was we said, well, at 80 inches, so LeBron is just below 4 standard deviations above the mean. So we kind of just said, here's LeBron right here. And obviously, his height is way, way, way above the mean. More than 3 standard deviations, almost 4 standard deviations above the mean, and we judged that by the 80, and look on our scale, where would 80 be? Oh, about right here. And then we did the same thing for Danny DeVito, and we said 60 inches, so here's 3 standard deviations below the mean. We have to go a little bit below that to find where Danny DeVito would be, and there's Danny. Okay, but we can be more accurate than just kind of estimating, eyeballing where they would be. We can calculate their z-scores. So let's do that. For LeBron then, we would say that his z-score is equal to, remember our formula is x minus mu over sigma. So the value of interest is LeBron's height, 80 minus 69, and notice we're going to get a positive number here, above the mean, positive. We're in the positive direction, so our x has to come first when it's larger than the mean. That means we'll be above the mean. Divided by 2.8. And for LeBron, we get 3.93. And that should make sense because we said he's almost to 4. Very, very close to 4. Now let's calculate a z-score for Danny. Use the same formula. I won't rewrite it this time. But again, we put Danny's height first minus the mean. Notice now I'm going to get a negative number for a z-score because Danny's below the mean, divided by 2.8. And for Danny we get negative 3.21. So we said he's more than 3 standard deviations below the mean, just a little bit past that at negative 3.21. Okay, so this is what we're going to want to do when we have a data set that does not have a mean of 0 and a standard deviation of 1. In fact, those are extremely rare. This is usually what we'll need to do, is to convert to z-scores. Okay. Finally, I want to point out that the z-score here for the mean, let's make sure this makes sense. If we calculate the z-score for the mean, we'd say 69, that's the value of interest, minus the mean, divided by the standard deviation, and we get 0 divided by 2.8, which is 0, which should make sense now. Our mean has a z-score of 0.